Now, starting with hydrides. What are hydrides? First of all, we need to understand. Hydrides are the binary compounds of dihydrogen with almost all the elements, metals or non-metals, except noble gas elements. Alright, except noble gas elements, you can see it on the screen. These are formed under specific conditions because dihydrogen is less reactive chemically. Alright, it is not reactive, hydrogen is. So hence, due to that reason, it is being formed under some certain conditions. You will be seeing it in the due course of the chapter. The hydrides can be represented by the general formula EHX. E is any metal, non-metal, we can say that, and H is hydrogen, and X is any what you can say valency, like NaH, CaH2. These are the sodium hydride, calcium hydride, we can say that. So in this way, hydrogen combines with a number of elements to form binary compounds called hydrides. Got it? All the what you can see is that the main group elements, except those of the noble gases and probably indium and thallium, they do not form hydrides. All lanthanides and actinides form hydrides. Transition metals, they form hydrides, and to a lesser extent like vanadium, niobium, thallium, chromium, copper, zinc, they do not form hydrides to a lesser extent. Means they form hydrides, but they are not stable, we can say that. Got it? Now, so you understood what are hydrides basically. So these are the binary compounds. Binary means two elements, we can say that. So in sense it is said to be as binary compounds. So if you see the classification of hydrides, it is ionic or salt like hydrides, saline hydrides, it's also said to be as covalent or molecular hydrides, metallic or non-stoichiometric hydrides. It is stoichiometer, it has become non-stoichiometric hydrides, we can say that, or covalent hydrides or molecular hydrides, we can say that. Got it? And metallic hydrides is also called as interstitial hydrides. We'll come to it later on. Why it is called interstitial, we'll know it. So now these are the three types of hydrides. Now coming to ionic or saline hydrides, these are the hydrides formed between hydrogen and electropositive elements of group 1 and 2 belonging to S block. So S block elements, when they combine with hydrogen like sodium, potassium, calcium, rubidium, cesium, they form hydrides, we can say that. These are stoichiometric in nature, means they have the same what you can say molecular composition. They are said to be stoichiometric in nature, which means that the hydrogen of and the metal are combined in the ratio as predicted by their formula. That's it. They are symmetrical. In general, ionic hydrides are of crystalline nature, that is they have salt like structure like NaH, CH2, KH, etc., and are therefore known as saline hydrides. Now, ionic hydrides basically are formed by those metals whose electronegativity values are appreciably lower than that of hydrogen, which is 2.1. Again I repeat, ionic hydrides, these are formed by those metals whose electronegativity values are appreciably lower than that of hydrogen. The electronegativity value of hydrogen is 2.1. So basically alkali metals and group 2 elements, alkaline earth metals, they form ionic hydrides like BeH2, MgH2 and so on, we can say that. If you come to the properties of the ionic hydrides, you will see these are formed by transfer of electrons from the metals to the hydrogen atoms and thus contain hydride ion H minus, like LiH, NaH, CH2, BeH2, all these things. These are white crystalline solids and their crystal structure consists of ions. Yeah, they are made up of ions. For that reason they are called ionic hydrides. The density of these hydrides is higher than those of the metals from which they are formed. This is because the H minus ions occupy holes in the lattice of the metal without distorting the metal lattice. They occupy the holes. Holes means what? The vacant space. Vacant space, when the metals are arranged, the vacant space are there in that particular holes. These what you can say, the hydrogen atom occupies the space, the hydride ion occupies the space, not hydrogen ion atom, hydride ion occupies the space. So hence the density of these hydrides is higher than those of the metals, because one atom is occupying, means mass is increasing, so density will be more. Alright, they have high melting and boiling points and conduct electricity in the fused state, in the molten state, liberating hydrogen at the anode. If you go for electrolysis, then you will find that hydrogen is liberated at the anode and metals are liberated at the cathode. Definitely, because metals are negatively charged and here hydrogen is metals is positively charged and here hydrogen is negatively charged. Except LiH, they burn in air on strong heating due to the decomposition into hydrogen, which is inflammable. They react violently with water to form the corresponding metal hydroxide. With the liberation of hydrogen, they act as strong bases. Like NaH reacts with water to form NaOH and H2. So H2 gas is liberated, due to which what you can say, it reacts violently with water, we can say that, and they form strong base. NaOH is a strong base, KOH is a strong base. Like KH reacts with water to form KOH and H2. Calcium hydride reacts with water to form calcium hydroxide and hydrogen. Got it? So they are strong bases, we can say that. They are powerful reducing agent. Ionic hydrides, they are powerful reducing agents, especially at high temperature. How can we say that? NaH reacts with carbon monoxide on heating to form HCOONA plus carbon. CO2 reacts with sodium hydride upon heating to form HCOONA, sodium formate. In this way, many more reactions we can have it. Like SiCl4 reacts with NaH upon heating to form SiH4 plus NaCl. SiH4 is what? Silane. SiH4 is silane. SiLane, silane. Lithium hydride is rather unstable at moderate temperature. We can say that lithium hydride and lithium boron hydride, LiBH4. Alright, they are used as a reducing agent. We can say that they are used as a reducing agent. Now, how lithium boron hydride is formed? LiH plus B2H6, that is diborane. LiH plus B2H6, that is diborane, in presence of dry ether. Dry ether acts as an inert solvent here to form LiBH4, that is your nothing but lithium boron hydride, we can say that. Clear? So these complex metal hydrides are widely used as reducing agent, I said you, in organic synthesis. Alright, so this is about your ionic hydride, so to say. Now coming to what you can say, the covalent hydrides, so to say. Covalent hydrides or molecular hydrides, these are the binary compounds of hydrogen, we can say that, with non-metals belonging to P block. We can say that the non-metals belonging to P block. The most popular among them are the hydrides of carbon, which are known as hydrocarbons. Other popular hydrides which we come across are ammonia, NH3, water, H2O, hydrogen fluoride, HF, hydrogen fluoride, HCl, etc. Got it? So being covalent in nature, these have low boiling points and are mostly volatile in nature. They are mostly volatile. Got it? These hydrides usually consist of discrete covalent molecules which are held together by weak van der Waals forces of attraction, and hence they are called as covalent or metal molecular hydrides, they are said to be as. Basically, these covalent hydrides, let me tell you a little bit in details about it, that covalent hydrides or molecular hydrides are mainly found by P block elements and some S block elements like beryllium, magnesium primarily, due to the reason that the electronegativity difference between these elements and the hydrogen atom is quite small. Why covalent bond is formed? We have studied. Covalent bond is formed when the difference in electronegativity between the two atoms is very, very small. When it is large, more than 1.9, then it results in the formation of ionic bond, you know that. And if it is greater than, if it is less than 1.9, if the difference goes on decreasing and decreasing and decreasing, so covalent character goes on increasing and increasing and increasing. So here also same thing. The difference in electronegativity between the one atom and hydrogen, the difference in electronegativity is very, very small, which results in the formation of covalent or molecular hydrides. So in these hydrides, what we do is that we add the suffix N to the name of the hydrides. Like for example, PH3 is phosphine, PH3. Water is oxiden, H2O is otherwise known as oxiden. Ammonia is known as azane. This is the IUPAC name, mind it. But the common name is phosphine. For water we call it H2O is water. For NH3 we call it as ammonia. These are the common names. Got it? But the IUPAC name is, for PH3 we call it as phosphine. For water we call it as oxidane. H2O we call it as oxidane. And for ammonia, NH3 we call it as azane. We can say that. So what you find is that these hydrides, what you find, they are formed by direct combination of the elements with hydrogen, like N2 plus 3H2 in presence of iron as a catalyst, molybdenum as a promoter. You know that, you have read it in Haber's process. Gives ammonia, we can say that, 2NH3. Got it? Similarly, BCl3 reacts with LiLH4 in presence of ether to give B2H6 plus AlCl3 plus LiCl. We can say that. Clear? So in this way, they act as hydrides. Now properties, if you see, covalent hydrides is usually volatile compounds having low melting and boiling points, and also do not conduct electricity. Because covalent compound, they do not have ions, so hence they have low melting and boiling points. And they are basically gases or volatile liquids, we can say that, and hence they do not conduct electricity due to the absence of ions. Hydrides of group 13, that is BH3, LH3, do not have sufficient number of electrons to form normal covalent bonds, and hence are called electron deficient hydrides. Now you have read it in ionic equilibria. These are called as Lewis acids. They are known as Lewis acids. They are said to be as, because they are also electron deficient. You have studied. Got it. So similarly, hydrides of group 14, CH4, SiH4, GH4, PbH4 have exact number of electrons to form normal covalent bonds. Have exact number of electrons, and hence are called electron exact or electron precise hydrides. Alright, like CH4 and PbH4, we can say that. Hydrides of group 15, 16 and 17. Note it, hydrides of group 15, 16 and 17. Ammonia, PH3, H2O, H2S, HF, HCl, HBr, etc. have more electrons than required to form normal covalent bonds, and hence are called electron rich hydrides. They are called as electron rich because they have more number of electrons to form covalent bonds. So if it has got less number of electrons, it is called electron deficient hydrides, which is otherwise known as Lewis acids. And if it has got more number of electrons, it is called electron rich hydrides. They are known as Lewis bases. Got it? In short, I should say. So this is about your covalent or molecular hydrides. Now coming to your metallic or non-stoichiometric or interstitial, what you can say, hydrides, we can say that. Now interstitial, so D block elements are group 3, 4, 5 and F block elements on heating with hydrogen under pressure. Got it? It forms hydrides, and they are called as metallic or interstitial hydrides. Again I repeat, D block elements are group 3, 4, 5 as well as 10, 11, 12. Sorry, I said it, forgot to say you, 10, 11, 12 also. An F block element on heating with hydrogen under pressure, they form hydrides. In group 6, noted this, very important. In group 6, chromium alone form the hydrides. In group 6, I said you group 3, 4, 5 and group 10, 11, 12. In between I left 6, 7, 8, 9. Got it? In between I left. Got it? Because 6, as I am saying you, in group 6, chromium alone forms the hydrides, CRH. The metals of group 7, 8 and 9 do not form hydrides. In fact, the region of the periodic table from group 7 to 9 which does not form hydrides is referred to as hydride gap. They are known as hydride gap. These hydrides generally have properties similar to those of the parent metals and hence are called metallic hydrides. Alright. Now, these elements, that is group 7 to 9, they do not form hydrides because the interstitial space, interstitial means what? The vacant space which is being created between the two metals is so small that hydrogen atom cannot occupy that particular space. So hence it does not form, and if at all it forms also, it is unstable in nature. For that reason, elements of group 7 to 9 do not form hydrides, and element of group 6 only chromium form hydrides, CRH, we can say that. And why it is called metallic hydrides, I've said you. Once again let me tell you that these hydrides generally have properties similar to those of the parent metals and hence are called metallic hydrides. I hope you understood. Now, why it is called interstitial hydrides, I've told you already that the hydrogen atom occupy the space in between the two metal lattice, in between the two metal atoms. So those spaces are called as interstitial spaces, the vacant spaces produced between the two atoms. Got it? Produced between the two atoms, and the two metal atoms or three metal atoms or four metal atoms are kept, then the space which is being created between them, that is said to be as the vacant space or interstitial space, and hydrogen atom occupies that particular space, and hence it is called as interstitial hydrides. For that particular reason we can say that. Clear? So it does not produce any distortion in the metallic lattice. The metallic lattice does not have any distortion at all, we can say that. Clear? Now what you can say is that these interstitial hydrides may be also regarded as either alloys. It is also known as alloys in case of metals, we can say that. So they are hard. If you see the properties, they are hard, they have metallic luster, they are good conductors of electricity and have magnetic properties. The density of these hydrides is lower than those of the metals from which they are formed, since the crystal lattice expands due to inclusion of hydrogen. Yeah, they repel, no? So when you put an atom in between two or more atoms, then they are going to repel one another. Due to repulsion, the atomic size increase, and atomic size increases means volume increases. So density is equal to mass by volume. So hence density decreases. We can say that. So these hydrides are often non-stoichiometric. We can say that non-stoichiometric because the ratio between the atoms and the hydrogen is varying. It is not fixed. Under temperature and pressure they vary. So hence they are non-stoichiometric hydrides. Due to interstitial hydride formation, these metals absorb large volume of hydrogen on their surface, and the property is known as occlusion. Alright, this is known as, due to interstitial hydride formation, these metals absorb large volume of hydrogen on the surface. Like platinum, palladium, nickel, they absorb large amount of hydrogen. Like palladium can absorb rather I should say 900 times of hydrogen of its own volume. So hence this phenomena is called as, this property of adsorption of gas by metal is known as occlusion. It is known as occlusion. This is said to be as. Alright, so I hope you got it about the hydrides. You came to know they have metallic appearance and their properties are close related to those of the parent metal. I said you already, they are strong reducing agents, and metallic hydrides can be used for storing hydrogen. This can release the same whenever required, we can say that. Thank you very much.